Studying the Sun from a close-up angle would give us a better understanding of how our host star works. But that's almost impossible due to the intense heat on the Sun's surface, right? Well, the Parker space probe has defied all logic as it proves to be a modern-day Icarus, flying into the surface of the Sun. But the real question is, why hasn't the probe melted, being exposed to the million-degree heat on the surface of the Sun? Well, we've got all that covered in today's video as we look at how NASA's Parker Solar Probe touches the Sun for the first time. Over the last few decades, NASA has sent dozens of space probes into space to allow us to better understand how the cosmic bodies in our solar system work, all except one, the surface of the Sun, and for good reason. A mission to the surface of the Sun was practically unthinkable, as any space probe would simply melt coming anywhere near the surface of the star. But the Parker space probe has proved that it can be done. Launched on August 12, 2018, the Parker space probe took off from Cape Canaveral, Florida, on its mission to study the Sun. But what exactly was this mission? Mission objectives. Well, the mission was to make close-up observations of the Sun, studying the region of the star known as the solar corona, which is the outer layer of the Sun. The objective was to understand how the Sun's corona is over 200 times hotter than its surface, with temperatures reaching 1,000,000 degrees Celsius at the corona, while the lower surface reaches temperatures of just a few thousand degrees. The goal was to understand how energy and heat are transferred from the chromosphere at lower temperatures and achieve higher temperatures on reaching the corona. Parker also aimed to understand the origins and acceleration of solar winds, which course through the solar system at speeds of up to 1,000,000 miles an hour. These solar winds have significant effects on the Earth's magnetic field, causing phenomena known as space weather, which in turn affect satellites in orbit, as well as electronics here on the surface. The probe will fly close enough to the Sun's corona to observe these solar wind particles go from slow subsonic speeds to high supersonic speeds as they shoot through the solar corona and into the solar system. But in order to make these observations, the Parker probe was able to take on the Sun's heat head-on, using a few highly sophisticated instruments that protect it from melting in under a few seconds. Protection from the Sun. Protecting the entire probe and its instruments is a fairly simple yet dynamic solar shield that has a hexagonal shape and is strategically placed on the sun-facing side of the spacecraft. The shield measures 2.3 meters in diameter, which is wide enough to shield other scientific instruments from direct sunlight and heat. The solar shield was designed to be over 11 centimeters thick and is made with two distinct panels of carbon-carbon reinforced composite steel, each with a lightweight carbon foam core, also measuring over 11 centimeters thick. This combination of carbon layers is able to withstand temperatures reaching 2,500 degrees Fahrenheit on the Sun's surface, while keeping the probe's instruments at temperatures below 100 degrees Fahrenheit. The shield is covered with a white alumina surface, whose reflective nature ensures a minimized level of heat absorption. With the broad surface area and diameter of the solar shield, the probe's scientific instruments are situated well behind the shield's shadow, protected from direct radiation and heat from the Sun. If the shield wasn't present, the probe would be just like any other space probe, and at this proximity to the solar surface, it would melt in under seconds and cease to be operational. With the Parker probe having to signal back data to Earth, which takes about 8 minutes to reach us, the probe would have to maintain a constant angle to keep the antennas shielded from direct heat and radiation. As such, the spacecraft is fitted with several autonomous protocols, which it employs to protect its instruments from melting instantly. The probe is fitted with 4 distinct light sensors, which it uses to detect the slightest trace of direct sunlight breaching the shield's limit, probably due to a slight shift in the probe's angle. These sensors then signal the probe to engage its mini thrusters to reposition the spacecraft such that the probe's instruments are all safely behind the shadow of the solar shield. The team at NASA describes the quick and witty response of the Parker space probe as the most autonomous spacecraft that has ever flown. While the probe aims to avoid direct sunlight from reaching anything but the solar shield, it also uses solar energy to power its instruments. The probe uses a primary photovoltaic solar array when it is within a safe distance from the Sun's surface, as even this array would be destroyed upon direct contact with the heat and radiation. As such, the probe uses a much smaller secondary solar array to power the spacecraft through its closest approach to the Sun. The secondary array doesn't work alone, as it uses a pump fluid cooling system to maintain its operational temperature during its encounter with these high-temperature solar particles. During its closest flyby to the Sun's corona, these primary solar arrays will be exposed to 25 times the amount of solar energy received here on Earth. Temperatures will be well over 2,500 degrees Fahrenheit, but its dedicated cooling system will maintain the solar array's nominal temperature at 320 degrees Fahrenheit and below. The spacecraft uses a flow-through cooling system that employs the use of pressurized deionized water, which is one of the few liquids capable of handling the fluctuating temperatures experienced in such intense environments. Parker's instruments. While the probe is protected from the intense heat of the Sun, its instruments can now go to work in observing the energy and heat processes ongoing since the birth of the star. The spacecraft employs the use of 4 distinct instruments in its observation. Parker uses its solar wind electrons, alphas, and protons investigations, or SWEEP, in measuring the abundance of solar particles present at every region of the Sun's surface it encounters. It measures the properties of protons, electrons, and helium ions to determine how and why the solar wind moves the way it does. Parker also uses its Wide Field Imager for Solar Probe Plus, or WISPR, which is a telescope used in producing complex 3-dimensional images of the solar corona, as well as the inner heliosphere. This will enable scientists on Earth to build 3D image models of the solar wind as well as solar shock waves that burst past probes constantly. During its 5th flyby through the Sun's surface, Parker was able to capture a live image of the solar wind using its WISPR instrument. The footage shows solar particles gushing past the spacecraft in spectacular fashion, as we've never seen before. The probe also has its Electromagnetic Fields Investigation Instrument, or FIELDS for short. It uses this instrument to measure the flow rate of solar shock waves that move through the Sun's atmospheric plasma and into the solar system. It uses antennas that stick out of the spacecraft beyond the limit of the solar shield to carry out its readings. These antennas are made of niobium alloy, which is an element capable of withstanding intense temperatures well beyond the 2,500 degrees Fahrenheit experienced around the Sun. Parker's final instrument is the Integrated Science Investigations of the Sun, or ISOIS, which it uses to measure solar particles in real time as they exist on different layers of the Sun. The instrument measures particle life cycles to determine their origin, how they become accelerated and shoot out into interplanetary space. Future missions. The Parker space probe is designated to perform 24 orbits around the Sun using repeated gravity assist maneuvers at Venus. This is meant to gradually decrease its orbital distance from the Sun's surface over its 7 years mission period. During its 10th flyby in November of 2021, the probe was able to achieve top speeds of 103 miles per second, accelerated by the Sun's powerful gravitational pull, making it the fastest speed achieved by any man-made object. Successfully performing 14 of these orbits so far, the Parker space probe will make its closest approach to the Sun at speeds of approximately 430,000 miles per hour, breaking its own record for the fastest speed achieved by any space probe. The probe will continue on its planned trajectory, and during its final 3 orbits, which are set to take place sometime in 2025, the space probe will come within less than 3.8 million miles of the Sun's surface. This will bring it to a point where it could observe the transition between denser solar particles as they become heated to extreme temperature within the solar corona. Studying data from the Parker space probe will enable scientists to understand the weird but fascinating heat and energy distribution on the Sun's surface. This will help us better understand and possibly predict phenomena like massive solar flares and how they interact with the Earth's magnetic poles. This will serve to improve space weather forecasting and facilitate improved preparedness for undesirable solar activities. Do you think the Parker space probe will make it to 2025 or be overcome by the Sun's intense heat? Let us know in the comments, and we'll see you in the next video.